Okay, so we're going to continue on in Module 6. So the first part of Module 6, we looked at trusses, and that was the last time that we were together. We saw how we could use MD solids to help us with that. And we also showed how to do manual calculations. So now we're ready to look at the second half of Module 6, which is going to be looking specifically at frames and machines. Okay, so I already have my guided notes underneath my camera, so we're going to go there, but you can also download and print this off, or if you got a copy the last time we were in class, then you do have the hard copy as well. So I'm going to go underneath my camera here, and the guided notes that I have are going to be handout number 2, and this is going to be on frames and machines. The section in the handout that we have for this chapter, this is that chapter 6 handout, you're going to notice starts on page 119, and the frames and the machines are like in that second column starting there. Now you can take the time to read this section, and I encourage you to. I'm not going to go into all those details, but this guided notes sheet kind of helps us to summarize the important things that we want to make sure that we know, and we'll be looking at some of the illustrations. So as we look at section 6-7, frames and machines, there's some fill in the blanks here. So it says a blank is a rigid structure that is designed to support external loads. That's going to be a frame. Okay, a frame. Similar to trusses, but the forces can be applied mid-span of a member. If you recall, when we looked at trusses, a couple of rules about trusses were that, number 1, you could only put any loads at the joints, okay? Also, a truss had to be attached on its end at the joints. Frames can be attached anywhere along any one of the members. So that's what makes them distinctly different than trusses, okay? Now, we'll be solving for reactions to supports on the entire whole frame, just like we did for the trusses. And then we're gonna, and then what we're gonna do is we're gonna take it apart and look at the internals, if you would. All right. Now, it says machines, on the other hand, are designed to transmit loads and forces rather than to support them. So, so in the second half of chapter 6, we're going to be looking at both of these. So frames and machines, and we're going to be looking at frames first. Now you'll notice down here, there is a procedure for going through and solving frame and machine problems. So the first thing is going to be similar to trusses. We're going to draw our free body diagram as a whole, machine or frame. And we're going to include our convention there, as it says, and we're going to determine the reactions at the supports when it's all together. Now, we're going to find that at times we might not be able to solve it all, and that's okay. And I'll show you how we can proceed anyway. But we try first to get everything, because we'll be able to kind of come back and fill that in as needed. Then what we're going to do is, once we have, exhausted the reactions at the supports that we can solve for, then we're going to break into the individual members. So if you recall from trusses, that was looking at each one of the individual joints. But now we're actually going to look at the individual members themselves. So that's going to look a little bit different. We're going to include any applied loads and all the reactions at the supports where they were applicable. We're going to then look at internal pin connections. So that means that there's going to be X and Y reactions. And when we move from one member to the next, we are going to change the direction of the forces at the reaction, or at the supports. We are going from one to the next. We're going to change direction of the reactions. And that'll, again, reactions. That'll make more sense when we do a problem, which we'll do very shortly. And then when you get to that last member, everything should be in equilibrium, or like when we sum our forces in the X or the Y, everything's going to be equal to 0, just like we were anticipating with our trusses. So let's just look at a kind of a progression, if you would, of this process. which is going to be found on the following page. This is page 120 at the bottom, okay? Now, as we look from left to right in this figure 624, the very first part A here of this figure, we kind of look here. This is the frame that we're looking at. This is a together frame. You'll notice that some of those differences that we talked about. First of all, we don't have to attach to another member just at its ends. So point E here and point B are within the individual members, okay? You're also going to notice that we don't have to have our forces or our applied loads at the joints like we did for trusses as well. So again, distinct differences that we see there. But you see that we have the entire frame together. So we're going to draw a free body diagram of that frame, and we're going to try to find the reactions at the supports. So the two supports that we have as we look at the original illustration, we've got a roller here at D and a pin at A. Okay, so we would try, as we have the whole frame together, this is part B of this figure, we would try to solve for those reactions at the supports, okay, using our equations of equilibrium that we're used to. Now, we would see how we would do. Like I said, it's if we can't solve it, it's okay. And then we just kind of go to the next step, which would be then breaking the frame into the individual pieces, okay? And once we break it into the individual pieces, then we can start looking more closely at each one of the individual items that we need. Now, when we break it into its individual pieces, we're now going to start seeing the individual pin reactions. So you'll see here at C where the horizontal member meets with the vertical member, right there, there is a pin at C. So you'll notice that we have a CY and a CX. Those are internal pin reactions, and we recognize them on the individual members. But when they're here, when the entire frame is together, they react one member on the other, so they're internal, and that's why we don't see them as external forces. They're internal to the frame. But when we pull it apart, that's when we want to see it. Now, you might ask, well, why are we interested in that? Well, the reason we're interested in those internal forces that are at each one of the pin connections is because now when we know what needs to be supported, we can appropriately size the fasteners or whatever the means to keep that together is going to be. And that's a strength of materials problem, all right? But we're doing the statics here first to identify what are those forces that are present so that we can safely fasten it together and be able to support what we need it to, okay? You'll notice that same thing is on the next member and then the other one. Now, that part where I said we change the direction of the reactions, okay? So part C here, when we move from one member to the other. So for instance, if it's an applied load like W, okay? It stays in the same orientation. If it's a reaction force, okay, like at A and at D, those are considered applied loads. They stay in their appropriate directions. But when we are an internal pin, like C, okay, when we start seeing the X's and the Y's, if we're showing it Y up and X to the right on one member, the member that it connects to, it's going to be the direct opposite. So we change the direction when we move from one to the next, one member to the next, okay? Same thing, for instance, at E. E, you'll notice, is this member right here. So it attaches up to that horizontal member. On the angled member, it's pulling away. And then you'll notice on the horizontal member, it's going in the opposite direction. So again, changing the direction when we move from one member to the next, okay? And I'll walk you through that as we do our example, okay? And then once we break it into its separate members here, we use our equations of equilibrium on each one of the members to solve for any unknowns. And then we're done when we find all of the reactions, okay? So again, we're going to notice that we're not going to be learning anything new here as far as information, but we're applying the concepts that we've learned from, chapters 2 through 5 now to, how to solve frame problems. So let's jump into an example. as I look at my guided notes and I'm on page 2, we're going to now look at example 6.7, and this is going to be found on page 122. Okay, so I'm going to move here. Oops, actually page 121. Oh no, 22. 6.7. Yes, it is. I'm skipping over that first example. We're going to go to the next one. All right. So the example we're going to look at is going to be 6.7. Okay. The problem statement is here on the bottom of page 122, but the illustration for it, or the picture, is going to be at the top of the next page. This is the frame all together. Okay. And this is on page 126. So illustration A is the original, and then the other ones here are going to be referenced throughout. Okay. So this is the frame that we want to work with. So the problem statement, kind of scooch in here, says the frame shown in figure 627A is supported by a pin at A and a roller at E. Find the components of all the forces acting on each member in the frame. Okay, so if we go back to our procedure, it's really, I like to say we're solving a frame problem, and that's a complete frame problem. The first thing we're going to do is we're going to draw a free body diagram of the whole together frame, and then try to solve for all the reactions of the supports when it is together, just like we did on the trusses. So that means we need to draw a free body diagram. Now, this is going to be a time when we are going to draw the thickness of the members. And the reason we're going to do that is because we need to distinguish from when it's an entire member that goes all the way from C down to E and C down to A. Because if we just draw a straight line and put the points along it, it's hard to tell if it's individuals, like from C to B, or if it's going to be, the whole thing. So you'll notice here that all the free body diagrams show thickness so that we can see the extent of the actual member itself. So what we're going to do is we are going to draw our free body diagram, again, adding thickness to the members so that we can see how, if they're continuous or not. And you'll notice at A here, we have a support. This is going to be a pin support. And at E, we're going to have a roller. Something I want you to notice is that there is a difference here of 1 foot. So E is not in line with A. There is a 1 foot difference vertically in E to A. Okay, that's going to be important as we, as we work with creating our reactions that are supports. So I am going to I'm going to leave this up because I suspect that some of you might not have this printed out, and that's okay. That's why I have it here. And then I'm going to draw the free body diagram. So the free body diagram is here. This is the illustration, but I'm going to get my free body diagram going on my paper, and then you can kind of get yours going too. Don't forget your convention. Now remember, free body diagram, we're keeping everything together here because we want to try to solve for the reactions at the supports when the entire frame is together. Okay. You want to add all your forces, all of your distances. And then those reactions at the supports that you're expecting. and then any applied loads as well. I'm just going to use the direction of that they're assuming, and then for the reaction of the supports, and then we'll confirm those as we work the problem, as you know. Let's see here, 6,000, 600. To all my dimensions. Oh, and then the 1 foot. Oh, how many should it? And add my convention, don't forget that. So my free body diagram looks like this. This side. Okay. Give you a little bit more time to get your details in place. And as you're looking at it, I did not identify, anything but kind of the overalls here. So I didn't put B and D in place because again, we're focusing on calculating the reactions at A and at E. So I just kind of put the overalls in place and then the dimensions that were, pertinent to where the loads were in relationship to those 2 points. All right. Does anybody need more time? I'm going to pull the chat out just in case. All right. If not, then we will move to the next step, which is going to be calculating the reactions at the support. So again, we're going to focus on what is AX, AY, and EY. So as we know, we're going to use the equations of equilibrium. So when we look here, I'm going to start by just kind of using that one that we're familiar with. A lot of times we start with some of the forces. I wrote that one. Some of the forces in the X are going to be equal to 0. So now we want to look, okay, what are my horizontal forces? And then according to my convention, identify the positive and negatives. So starting by summing the forces in the X, I'm going to take AX is going to the right. That's what I assumed. And I also have 1,000 pounds going to the right. So I have AX positive plus 1,000 pounds. Make sure you put your units in. That's my sum of my forces on the left-hand side here, and I'm going to set that equal to 0. So to solve for AX, I'll leave AX where it's at. AX is going to be equal to a negative 1,000 pounds. Okay. Now you're going to notice here that we have a negative value for the 1,000. So all that means is, as we know, when we get a negative as our final answer, oops, we assumed the wrong direction for the value that we have here. So all that means is I'm going to take my eraser, okay, go over the top here, and I'm just going to switch the direction for AX to go to the left instead of to the right. And it actually makes sense. If our applied load of 1,000 is going to the right, in order to support that so that it doesn't move, AX has to go to the left, right? So it makes sense. So we're going to make this positive, and we're going to make sure that our arrowhead is pointing to the left. So simply erase. You don't have to redo any of this math here. It's just part of the process. And then we're going to put a box around that because that is a final answer. That's one of our supports. So we know that to be 1,000 pounds. So I'm just going to put 1,000 pounds by AX. Now we need to solve for AY and EY. Now, since there are two in the Y, if I do my sum of my forces in the Y equals 0, and I can, I'm going to have two unknowns. So what I'm going to do instead is I'm going to do sum of my moments, because I know with a moment, I can eliminate one of those unknowns. So I'm going to sum my moments around a point. I have to decide which one. Now, since I'm trying to find AY or EY, somebody let me know in the chat box, what point we should sum around. Should it be A or E? You want to go around A? Sure, let's do A. So we're going to put our A here. And then go ahead and sum your moments. Put your finger on A here. That takes care, that eliminates, if you would, AX and AY. But now we've got some other offset forces so that we can solve for EY. So go ahead and sum your moments, okay? So you should get EY equal to 1,200 pounds. And we ended up with a positive value, or at least I did, which means and confirms that the direction of EY is correctly directed. Okay, so I don't have to do any changes here. So this is equal to 1,200 pounds. Okay. Any questions on that? Did everybody get their, force times distance to work out so that you got 1,200 pounds? Okay. All right. So then the last one that we need to solve for is AY. So I've got some space here. I'm going to do my sum of my forces in the Y equals 0. So I've got a positive AY. I just look at forces in the Y direction. I've got a minus 600. And I've got a positive 1,200. So my EY now is a known value equal to 0. So I can combine these two on the left-hand side. That'll be 600, right? Positive 600. So my AY is going to be equal to a negative 600, right? Positive on this side, move it to the other side, it becomes negative. Uh-oh. Remember, we never, ever leave a negative answer as as our final answer. So we're going to make this positive. We do two things. And then we're going to go up here and we're going to change the direction of AY to be down. Okay. And then we're going to put a box around AY. Any questions? All right. So that means that in this case, I'm going to put my 600 there. In this case, we were able to solve for all the reactions to supports. Okay. I'm going to tell you, sometimes you may not be able to. All right. And that's okay. You just get as many as you can. Now, the reactions at the supports, I'm going to tell you, these always stay in the directions that we establish in the problem and on this first step. So for instance, if we go back to our process, when we move from one member to the next, we change the directions of, I'm going to add the reactions at the pins, not the supports. Okay. And I'll actually add internal pins here just to give it a little bit more direction. Okay. The supports, which are AY, AX, and EX for our problem, stay in the directions we establish. Okay. Those are considered external forces. The pins are actually internal, like at C and at E and at B. Okay. So the forces that we see on this together free body diagram, they all stay in the same orientation, the 1,600 and the reactions at the supports. Okay. Now we're ready to pull it apart and find out what are the reactions at each one of the pins. Okay. The pins are going to be at C that hold the members together. At B, this is actually a point B, and at D. Okay. Now, what we're going to do is we are going to now look at each one of the separate members. So step number 3, I say, draw the free body diagram of member A, B, C to determine the reactions of those internal pin connections. So A, B, C is the vertical member right here. Okay. So we're going to draw that one first in this spot. So make it nice and big. We've got plenty of room here. So I'm going to go about like that. And again, I'm going to add the thickness here just because it's a frame member, so we can see it's a continuous member. So up here is going to be C. Down here is going to be A. And then, I don't know, right about just a little bit over half up. Wait, no. 4, 8 actually down. Right about there is going to be our B. Okay. We know the distance here between A and E is 5 feet, but we also have to add our external force, 1,000 pounds. Okay. Between B, so I'm going to kind of draw just a little line here. This is going to be 4 feet and then 4 feet up to C. Okay. At A, we're going to use the same magnitudes and the same directions as we establish in the together frame. So we have AX going to the left as 1,000. AX is equal to, and then we had AY going down at 600. Okay. Now, on this member, we want to also add now these internal pins. It's like we took it apart and we're now going to look, what are the reactions at the pin connections, the internal pin connections, which are at C and at B. Because they are pins, they're going to both have an X and a Y. So I'm just going to establish, I'm not going to necessarily know exactly what the value is going to be at this point or what the direction is going to be, but I'm just going to assume a direction. And I'm just going to use what they're using on the diagram as well. So they're showing CX going to the right and CY going down. They're also showing BX to go to the right and BY going down. And again, we will establish, I probably would change that up a little bit. We will establish directions and magnitudes, you know, with the math that we do using the rules that we've been using. Okay. All right, so those are all the forces acting on this body. The external loads due to the external support, if you would, and then the 1,000 pounds that was identified, and then these are the internal pin reactions at B and C. So we need to find BX, CX, BY, and CY, okay? So we're going to start by, seeing if we can use any of our equations. Well, we are going to use our equations of equilibrium to find any of these values. So let's just start by looking at, I don't know, some of the forces in the x, right? Some of the forces in the x equals 0. Let's see what we've got. We've got a positive cx. We've got a positive 1,000. I'm just kind of going down. We've got a positive bx. And we've got a minus 1,000, and that's at ax, okay? Those are all of the forces in the x direction set at equal to 0. These two kind of cancel each other out, right? Positive and negative, all right? That makes sense. So we end up with cx plus bx is equal to 0. Two unknowns, right? So we're just going to kind of leave it there, all right? We can't, it doesn't look like at this moment we can solve for those with that equation. Let's do the same thing in the y direction. I'm going to leave a little room here. I'm going to say, okay, some of my forces in the y direction equal to 0. So again, we're going to look. I've got a negative cy, a negative by, and I've got a negative 600. Okay, something's got to be positive there, but that's okay. So I'm just going to put the 600 to the other side, and we're going to say, okay, and we're going to leave our directions as is. Minus cy minus by is equal to 600 pounds, okay? There's one more equation of equilibrium we can try. So we can't solve this. There's two unknowns. So we might as well try sum the moments, right? Sum our moments, and we have to pick a point. I'm going to give myself a little bit more room between. I'm going to go a little bit lower. Sum my moments. So I'm going to either pick B or C. So I'm just going to pick C just because it's at the top here. That means I can eliminate CX and CY. This is in line. So BX is not going to cause a reaction, but I'm sorry, BY is not going to cause a rotation, but BX will. So that'll be there. So let's kind of see how this works out. So I'm at C here. I'm going to rotate in the direction of the 1,000 to start as I'm coming down. So I'm going to go C is equal to 0. And my first one here is going to be 1,000 pounds times perpendicular distance from C is going to be 4 feet. Okay. It is going to rotate counterclockwise. So that would be positive out front. So that looks good. If I put my finger back on C and I pull in the direction of BX times, this time it's going to be 4 plus 4, so it's going to be 8, is going to be my perpendicular distance. It's also pointing so that it would rotate counterclockwise, so that'll be positive out front as well. And then the last one that I have here is going to be AX. AX is 1,000 pounds. See, 1,000 pounds times perpendicular distance of 8 plus 5, so that's 13. Okay, and it is going to rotate clockwise, so that's going to be negative. All right, those are all the forces causing rotation, so I set that equal to 0. In this case, I just have one unknown, which is good. So I'm going to solve for BX. All right, so now I'm going to be 1,000 times 4. Okay, and then I'm going to subtract 1,000 times 13. And that's going to be negative 9,000 on this side. Pound feet plus BX times 8 feet. Okay, equal to 0. I'm going to put the 9,000 on the other side. So BX times 8 feet is equal to 9,000 pound feet. I'm going to divide both sides by 8 feet. So my BX is 1,125. And that's going to be pounds. Now, you'll notice that we ended up with a positive value. So that means the direction on member ABC for BX is correct. So it stays in that orientation, and this is going to be 1,125 pounds. Okay. Now, that means that we can go up to the top here and use our 1125 in this equation to solve for CX. So we're going to say, all right, CX plus 1125 pounds is equal to 0. Move that to the other side. CX is going to be equal to a negative 1125 pounds. Well, that's a problem. We know that if we have a negative number, we assumed the wrong direction. We do not leave a negative. We have to fix this each time. So we're going to make this positive, and we're going to change the direction here from going to the right to going to the left. So make sure you update it here. That's really important, okay? Because remember, on these internal pins, they have to be correct so that when we move from one member to the next, we're going in the right, we have the right direction. Okay, so we've got CX also as a final answer. We can't do the Y's yet though, right? Because they were, in the same equation. So we're going to have to wait. So that all that means is if we have anything that, let me put it's equal to 1125 pounds here. If we have anything that is left on a member, that's okay. We'll come back to it because there's a good chance on one of the next members we will be able to solve for it. Okay, so we're just going to leave our CY and our BY as is here, and we'll come back and we'll be able to fill this in. Okay, so the next thing that you're going to notice that we do is we're going to draw a free body diagram of member BD by itself to determine the reactions of those internal pins. So if we look back at our free body diagram, BD is right here. So we're going to draw just that member, okay? Now, if you need to go back and look at a little bit more detail, we're going to see here that member B to D, this 600 pounds is being suspended right in the middle of it. So 3 feet from B and 3 feet from D. Okay, so it's right down the middle. And then each of these are a pin reaction or a pin support, internal pin support. So it's going to be X and Y at each end. So I'm going to draw, make it a little bit taller up here, a little bit closer. So I have room to do what I need to do. So this is B to D. B, here's B. And then I have my 600 right in the middle coming down. This is 3 feet on this side. This is 3 feet on that side. And I know that there is a pin reaction here at both of these places. I have to put an X and a Y in place. Now, we look back to our original member. We already confirmed the direction on this member to be 1,125 going to the right. So as we said, for internal pins, when we go to a new member, it has to go in the opposite direction. So that means that our BX is going to go to the left on this member. If it's confirmed and going to the, to the right on the member above, then it's going to switch directions on the next one. And this is going to be equal to 1125 pounds. Okay. Now, the Y direction, we assumed going down on this member. Okay. So we're going to keep it the same. So we're going to assume it going up here. So if it's down on one, remember, we change it on the other. So that means over here, we're going to assume that this is going to go up. So this is going to be BY. We didn't calculate it up here yet. We don't know its magnitude, and we're really not sure of the direction because we weren't able to confirm it with a positive value like we were the other ones. But we're just going to go with what we have, and we'll see if we can confirm it here. So that's BY. Then you're going to notice that we have to fill in X and Y at the internal pin at D. Now, since BX was going to the left, the only other direction that's going to be in the X is going to be at D here. So I'm assuming it's probably going to go to the right. So we're going to say that this is DX. Okay. We have 600 going down in the middle. It's evenly distributed. We have BY going up. I'm going to assume dy going up, and we'll see if this works out to be okay. Okay. So now what we're going to do is we're going to use our equations of equilibrium to solve for the unknowns that we see here, which are by, dy, and dx. Okay. So I'm going to start by doing my sum of my forces in the x equal 0. I've got a negative 1125 pounds and a positive dx equal to 0. So only the horizontal. So there's only those two forces. So solving for dx, I'm going to say dx is equal to 1125 pounds. Okay. Positive value. So it confirms the direction that we put on. Okay. Some of the forces in the y, we're going to have two unknowns. So instead of jumping to that one, instead, I'm going to go to sum the moments around either B or D to eliminate one of them. So I'm going to say sum my moments around B equal to 0. I'm going to put my finger on B and I'm going to rotate in the direction of my offset forces. So I'm going to have 600 pounds times perpendicular distance, 3 feet. It's going to rotate clockwise. So that's going to be a negative out front. I have dy, that's going to cause rotation. So I'm going to have dy, which is unknown, times 6 feet. Okay. And it is going to rotate in a counterclockwise direction. So that's going to be positive out front. Set it equal to 0. All right. So now dy is our only unknown here. So we're going to solve for dy. So I'm going to multiply that together. That's going to be negative 1,800 pound-feet plus dy times 6 feet. Move that to the other side. Dy times 6 feet is equal to 1,800 pound-feet. 6 feet, divide on both sides. Dy is going to be equal to 300 pounds, right? And pounds are left over, it didn't cancel. And it kind of makes sense, right? If 600's in the middle here, we're expecting half and half to be on the other side. So to get our B value, we are going to say, I'm going to kind of scooch it in here, sum our forces in the y direction equal to 0. So now we've got By minus 600 pounds plus 300 pounds is equal to 0. So if we have negative 600 plus 300 on this side, this is going to be negative 300 here. So we're going to move it to the other side. By is equal to 300 pounds. Okay. And it's a positive value. So that means that the direction we assumed was correct. Okay. Now, because this was one of the values from the previous member, we can go back. If we know that it's going up on member BD, that means it is going down on member ABC. And we can say that its magnitude now is 300 pounds, right? 300 pounds. So going to this equation, we can now fill in the 300. So we have a negative CY minus 300 pounds is equal to 600 pounds. We're going to move the 300 to the other side. Negative CY is equal to 900 pounds. Now, we have a negative though, and we kind of suspected one of those was probably going to have to change. So that means that we're going to make CY positive here, but we have to change the direction of CY to go up on member ABC here, okay? So now it's confirmed going up equal to 900 pounds. And it makes sense. We've got 300 going down, 600 going down. So to keep this in balance and equilibrium, C has to go up. Any questions? So that's how you kind of go back and forth between them. So don't worry if you can't solve, like we couldn't solve for CY and BY when we first did this member, but once we go to another member, we usually can fill in some of those blanks and then go back and finish. So right now we've got 2 members done. We've got 1 more member to do. So if we turn the page, you'll notice that it says, all right, now we're going to draw member CDE to check for equilibrium. If you recall, our free body diagram has just the 3 members. It has CBA, CDE, and BD. So we've done this one and this one. Okay, so we know the reactions at C and D. We already solved for EY. So all we're looking for here is that everything balances out. Okay, so on our final spot here, we're going to draw CDE at the angle, identify each one of our pin reactions. So up here is going to be C, here is D, and here is E. Okay, so this is going to be C, D, and E. Now, E, remember, was a support, but of the whole frame member. So the reaction at the support as a whole is going to remain in the same direction. So EY was 1,200 pounds going up. It's just like any other applied load. Okay. Now, D and C were those internal pins. So we've got to look back. I'm going to do D first. We had DX going to the right on member BD, and we had DY going up on that same member. So when we switch to our CDE, we're going to show this going opposite direction. Same magnitude, but opposite direction. So the X is going to go to the left and the Y is going to go down. So we're going to have this way. This way. And we had 300 for the magnitude in the Y and 1125 here. Okay. And now we're going to go up to C. Okay. So if we go back and look at C here, the confirmed directions were CX going to the left, 1125, and CY going up. So on the next member, they're going to be opposite directions, same magnitude. So CX is going to go to the right. And that was 1125. And then it's going to CY is going to go down. I think it was 900, right? Now, as we look here, if we sum our forces in the X and Y direction, you can already see that they're going to come out to be 0. So sum the forces, we'll do the Y first equal to 0. We have a negative 900 pounds, a negative 300 pounds, and a positive 1,200 pounds. And I've got to set that equal to 0. We can see that indeed, this is going to be 0 is equal to 0. And then we're going to do the same thing in the X direction. Sum the forces in the X equals 0. So we're going to have a positive 1125, a negative 1125, and those are my only forces in the X direction. So I'm going to set that equal to 0. So then that's going to be 0 is equal to 0. So that means that everything came out and we're in equilibrium. So we're happy. So that's how we solve a frame problem. Any questions at the moment? Okay. So I'm going to stop the recording here.